Imagine a computer that doesn't end up in a landfill, but in your garden as fertilizer. We are moving past the era of rigid silicon to build processors out of living fungal networks. These processors can self-heal and solve complex problems. This is the transition to mycelium-based hardware. Beyond mere performance, our reliance on silicon has created an environmental disaster. By 2026, global e-waste production reached a staggering 75 million metric tons annually. These discarded devices are saturated with toxic flame retardants and non-recyclable materials that poison our land. Our current technological hunger is ecologically unsustainable. We are at a critical junction. To survive our own advancement, we need a fundamental shift in how we conceive, build, and retire our hardware. The solution to our computing crisis lies in nature. Introducing mycelium, the root structure of fungi. Mycelium consists of intricate networks of hyphae. These filamentous paths grow organically, creating complex, branching architectures. By treating these hyphae with specific biometallic compounds, we transition them into conductive organic circuits. These circuits allow us to perform complex computational tasks using organic matter, shifting the paradigm of hardware design. Hyphae are the fundamental thread-like structures of mycelium. In the context of next-generation biocomputing, these filaments serve as natural, organic wires capable of conducting electrical signals. Unlike static silicon circuits, hyphal networks are highly dynamic. They can grow and reshape themselves in real time, rerouting data pathways to maximize efficiency based on computational demand. By leveraging these adaptive growth properties, we transition from rigid, finite architecture to organic systems that evolve alongside our computational needs. We are currently witnessing a shift in hardware production. We are replacing toxic chemical lithography with grow-in-place technology. Instead of etching silicon chips in sterile cleanrooms using harsh, hazardous solvents, we now utilize biological processes. This method allows us to grow custom circuit architectures naturally, effectively eliminating the massive environmental footprint of the semiconductor manufacturing industry. In traditional silicon computing, data pathways are rigid and fixed. Like a city with locked roads, information must follow preset routes. Mycelial processors operate differently. By mimicking the foraging patterns of slime molds, they continuously sense their environment to grow the most efficient path in real time. This biological approach allows the processor to solve the traveling salesman problem at the hardware level, rerouting data instantly to avoid congestion or damage. By abandoning fixed architecture for a living network, we unlock massive gains in computational efficiency and connectivity. Silicon circuits are rigid and fragile. If a single path breaks, the entire logic flow fails. In contrast, mycelium networks are inherently resilient. When a node is damaged, silicon hardware stops working immediately, but mycelium detects the fault and responds. The network grows new hyphae, rerouting the signal around the damaged area. This biological self-healing process drastically extends the lifespan of the device. At the end of its life, a mycelium processor enters a unique phase. Rather than being dumped, it is triggered into a dormant state, safely shutting down its logical pathways. When placed in compost, the structure naturally breaks down. Instead of leaching hazardous heavy metals, it enriches the earth, cycling nitrogen and organic matter back into the ecosystem. Researchers at UC Berkeley and ETH Zurich have successfully engineered the world's first fungus logic gate. This breakthrough transforms mycelial hyphae into functional electronic circuits. By manipulating biological junctions, they achieved Boolean operations. Inputs from mycelial networks propagate signals to a central organic gate, determining binary outcomes. While currently constrained to low-power IoT applications, this gate serves as the fundamental building block for future self-healing biocomputing hardware. In the Nordic regions, pilot data centers are currently testing a revolutionary hardware configuration, the BioRack. These racks replace standard resource-heavy silicon motherboards with sterilized, bioengineered mycelium substrates. By using fungal networks, these facilities achieve rapid hardware turnover cycles. Because the boards are organic, they offer a low-impact solution to the high-frequency replacement needs of modern computing architectures. We are currently transitioning into a hybrid era of hardware design. In this model, high-performance silicon cores continue to handle the raw heavy lifting of intensive computation. Complementing these cores, we grow mycelial networks that act as a sophisticated nervous system. These organic structures are responsible for managing power distribution and performing real-time fault detection. By integrating the reliability of silicon with the adaptive, self-healing properties of mycelium, we create a hardware environment that is significantly more resilient and energy efficient. A revolutionary shift in hardware production has arrived: processor growth kits. Instead of traditional manufacturing, companies now order concentrated fungal cultures. These kits allow for incubation on-site, where fungal cultures expand to form custom-shaped, circuit-embedded motherboards. This process eliminates the need for massive factory logistics. By growing hardware locally, businesses drastically cut carbon emissions associated with long-distance shipping and toxic industrial lithography. The economic shift toward mycelium-based computing is driven by a massive reduction in overhead. While silicon requires expensive, energy-intensive cleanrooms and toxic chemical processing, mycelium circuits are grown in controlled organic environments. Growing biochip substrates is 60% cheaper than traditional fabrication methods. By eliminating the necessity for cleanroom facilities and hazardous solvent disposal, the cost of entry for hardware production is dramatically lowered. This economic accessibility transforms the industry, allowing smaller players to enter the hardware market and fostering a new wave of sustainable, low-cost bio-innovation. The transition to biocomputed hardware is backed by hard data. Life cycle assessments from 2026 reveal a staggering 92% reduction in carbon footprint compared to traditional silicon manufacturing. By bypassing energy-intensive cleanroom fabrication, mycelium-based semiconductors offer the most viable path toward a truly sustainable technological future. This ecological advantage stems from the elimination of toxic solvents and high-energy chemical lithography. Our biochips grow at room temperature, creating zero heavy metal waste. In the quest for reliable hardware, we find that mycelium-based chips outperform traditional silicon in high-stress, high-impact environments. Unlike silicon, which is static and prone to permanent failure upon physical trauma, mycelial networks are regenerative. Because these chips can graft new hyphae to bypass damaged sections, they have demonstrated 30% longer active uptime than their silicon counterparts. By the year 2030, the shift toward organic computing will reach a significant milestone. Analysts project that 15% of all consumer electronics will be powered by mycelial substrates. This adoption will be most rapid within three key sectors: high-utility wearables, medical monitoring devices, and interconnected home sensor arrays. These specific areas prioritize low-power efficiency and environmental sustainability, making them the perfect candidates for the biometallic hyphae networks of the future. As this trend continues, the infrastructure of our daily lives will transition from static silicon to a self-growing, living technological layer. As Dr. Alina Vance notes, we aren't just building chips, we are curating living environments. This marks a profound shift in hardware design. Traditionally, we relied on rigid, static silicon grids. These were manufactured in sterile environments, fixed in their purpose, and unable to evolve. Now we have moved from manufacturing static tools to cultivating organisms that calculate. Mycelium-based semiconductors allow us to grow custom logic paths. We are effectively curating a living digital ecosystem. By manipulating fungal growth, we create hardware that is dynamic, self-repairing, and ultimately an organism. If a computer can grow, adapt, and heal itself like a biological entity, at what point does it cease to be a tool and start being classified as an organism? Traditionally, a tool is defined by its static nature, a dead object designed to serve a fixed purpose. An organism, by contrast, is characterized by its capacity to heal, adapt, and evolve. When we introduce mycelial networks, hardware that grows circuit paths in response to environmental needs, we blur this divide. Is autonomy the trigger? Is it the presence of metabolic cycles? Or does hardware become alive the moment it begins to care for itself? This suggests that the definition of a tool may soon become an artifact of the industrial past, replaced by hardware that exists in a state of symbiotic partnership with its user. While mycelium-based hardware represents an incredible breakthrough in sustainability, we must acknowledge its current limitations. These systems are not yet capable of matching the extreme clock speeds required for high-frequency gaming or large-scale AI model training. The hardware is optimized for low-power ambient computing rather than raw computational throughput. We are prioritizing efficiency over speed in this early stage of biologic gate development. Furthermore, scaling organic logic gates to the density of silicon creates stability issues. Biological volatility means that signal consistency can fluctuate as the substrate grows, creating unique challenges for standard binary logic operations. The goal is not immediate replacement, but rather augmenting hardware ecosystems to handle specialized, energy-efficient tasks where silicon's rigid structure falls short. Scaling mycelium computation requires addressing the speed at which signals propagate through fungal networks. Natural hyphae are limited in their data transmission rates. To solve this, researchers are doping mycelium with nanoconductive polymers. This enhancement dramatically increases the conductivity of the fungal network. By integrating these polymers, we achieve high-speed data transmission, bridging the gap between biological potential and practical computational needs. Hardware design is undergoing a fundamental transformation. We are shifting from the rigid, static world of electrical engineering toward the dynamic, adaptive field of bioengineering. Designers now must account for biological variables. Instead of voltage and resistance, we specify moisture levels, nutrient access, and complex fungal growth patterns to shape our computing substrate. By mastering these growth cycles, we can cultivate logic gates directly within living mycelial networks. Hardware is no longer just built, it is grown, curated, and sustained.